Hello, listeners. Welcome to another episode of The Circuit. I am Ben Bajarin.
Greetings, Internet. I'm Jay Goldberg.
So, today we have an excellent topic and an excellent guest, a veteran of the semiconductor industry. Our overall topic, which sort of thematically makes sense because we actually haven't talked about this, even though we have gone into it in detail, is the abounding thermal problem coming to really everybody in the data center hyperscalers, even on premises, as we're going to run H100s and the rumor of future B100s being in the 1,000 watt range. A board of AMD systems is 750-ish, 760 watts. So you stack those up, we know we have a power and a cooling problem. And that's going to be our subject for today. I will let Jay introduce our distinguished guest.
So, our guest today is Carl Schlachte. And Carl, why don't you introduce yourself to the people?
Hey there. Hi, Ben. Hi, Jay. Thanks for having me. Yeah, Carl Schlachte. I'm kind of a startup guy. I've done about 9 startups now. Previous experience at places like ARM and Motorola and a whole bunch of other semiconductor companies in between. Spent the better part of the last couple of years at the company that we're going to be talking about today, Ventiva, where I'm the CEO and chief bottle washer and garbage can emptier and whatever else I do. That's kind of my background. I think it's also related to the stuff that both Jay and Ben are bringing up is we do see our opportunity in the thermal space, and there's a lot going on in that space right now. And I got to give you guys props for even talking about it, because it is kind of the unknown problem or the unspoken problem in everybody's uh, uh, consumer electronics / digital design right now. It's just so presumed a problem that it doesn't even get merited for a conversation anymore. So I'm super glad to be able to talk about it a little bit.
Excellent, excellent topics.
Yeah, because it's everywhere. That's the thing that really gets to me. You talked a lot about the data center, Ben, but it's like in our handsets. That's where I notice it the most. It's this big problem in PCs that we sort of just have come to live with, but it's TVs and game consoles and cars, right? Everything is getting a little too hot. We're running a lot of compute underneath everything, and that adds up. So,
Yeah.
so Carl, tell us a little bit about your company. Tell us about Ventiva.
Mhm.
Give us the origin story.
Well, so the origin story, there's kind of, I guess I would say there's kind of 2 origin stories. I think most honest startups would tell you there's the when we met and fell in love story, and then there's the after 15 years of marriage, here's what we figured out the relationship was really about story. Um, so our origin story is exactly like a lot of other startups. So there's some really good, cool work going on over at Purdue University on a principle with a really intimidating name called electrohydrodynamic flow (EHD), and that's really a principle that's been known for a long time of applying electricity to gas or fluids, and being able to use that electrical impulse to impart movement on the surrounding fluid. This principle has been around, like they noticed it, I don't know, 120 years ago. You could feel this breeze coming off of high voltage electronics, and nobody understood really how to harness it, or not only harness it, but also turn it into something that could be useful in modern electronics design. And by useful, that means scalable, meaning you can put it in very small things, very big things, the same basic architecture. It also means that you can build it cheaply, in a manner that lets it get used in a bunch of spots. And you can build it in a manner that takes advantage of current electronic design principles, meaning I can throw it into a contract manufacturer and have them build these things by the millions, and get the learning curve stuff that we all know happens in our industry applied to things like thermal management. So if you can do all those things on electrohydrodynamic flow, you should have a winner. And that's what the company did That was the company's original ethos at the beginning. It took us a while to get there, but we did get there, and so now we get to use this stuff or we get to show this stuff deployed in a bunch of electronic devices that wouldn't otherwise get access to this kind of thing if we hadn't done our work.
And I'm sure it was just smooth sailing. You started the company, and the next week,
super smooth sailing, my friend. It was like we went from success to success over a period of 10 years, and that is absolutely not what happened. I think one of my favorite questions for startup guys, because every once in a while you get fellow pals to go out and talk about what's going on in their particular entrepreneurial experience. And my favorite question is, what's your near-death experience? What's your favorite near-death experience? And the beautiful thing about Ventiva is we've had about 7 of those. And so in each one of those, we kind of took away something from it that made made a concrete difference in the end for our customers. I mean, my favorite one was, and actually, this is what I would consider. I mentioned this whole thing about what's the marriage after 15 years. That's really an origin story. Our origin story in that sense is after we've been going for a while, we were partnered with a company here in the Bay Area, and they brought us into their facilities, and we were going to build our ICE, what we call ICE, ionic cooling engine, into their Qi wireless chargers. Because high-speed wireless chargers, like a lot of things, have a heat problem associated with them. So we partner with these guys. We're developing semiconductors to go along with it. We're building prototypes. We got a list of 30 customers, all this kind of thing. And then this company gets bought and decides they don't want us anymore. They don't want to do anything about it. And now we've got like all our eggs in this basket. And then along comes COVID. And we get evicted from the building, and we don't have any of our equipment. And it was awful, absolutely awful. And what the guys here did, which was super wonderful, is believe it or not, we had actually been practicing for COVID lockdowns for about a month. Meaning, as a company, we made a decision: you're going to have everything you need at home in case we have to go into lockdown in order to try to get something going. So our guys actually went and started doing a lot of this stuff at home. And when we got kicked out of the building and I thought the jig was up, these guys are driving all around the Bay Area with plastic bins of parts. They drop it off at Gary's house. Gary would work on it. He'd drop it off at Rudy's house. And then it would go to Jeff's house. And eventually this culminates in everybody meeting up in a parking lot at Target in Milpitas. I am not kidding you. They put a box of donuts on the hood of the car, and they finished the build. There's like a mobile programming lab in some guy's trunk. They finished the build and they shipped the stuff off to customers. And that was 4 years ago. That to me is our origin story. That describes Ventiva to a T. But I think to bring it back to the kind of the global remit that you guys gave at the beginning. That also speaks to the size of the problem. We have customers depending on this pretty heavily now for some of their next generation type problems. And we had a bunch of folks here who weren't going to let them down. And they found a way to do it. And we continued on from there with funding, customer design wins, buildings, all the rest of it. Super cool.
Yeah. So maybe talk more about the space. I mean, I think there's sort of obviously, like, people don't know like a brand name that provides cooling systems. And I think a lot of people assume a lot of these companies design their own systems. Like, I'm sure most people will just follow the Apple narrative and say, hey, I mean, they do their own whatever, right? They design chassis that move air, whether it's fanned or not. They're involved. So maybe just kind of lay of the land. Who makes these things,
and how do they move?
What's that structure look like on those that provide these solutions?
Yeah. So, it's a great question. So I guess part of the interesting challenge for a company in a space like ours is that there haven't been that many options for cooling systems in general. The technologies that are out there for cooling any electronics, anything from your data center through to your laptop or your phone or anything else, rely on a couple of tried and true types of technologies that have been around for about 40 years. So things like, let's start with there's a thing called a fan. Everybody knows what a fan is. A fan is this electrical motor that has blades attached to the spindle, and the spindle spins, and those blades hit the air and they impart movement on them. So there's a mechanical process there for moving air. Most electronics that get really hot rely on some type of movement of the heat from point A to point B in order to get things done. So, or in order for the product to continue working. So that's one thing. There's another thing. There's things called heat pipes. Heat pipes are pieces of copper that have a liquid inside of them, and the liquid evaporates inside of them. And as it evaporates, it uses capillary action to move the liquid from point A to point B, where it condenses, and then it flows back to basically the hot spot. I'm grossly oversimplifying here, but you're talking about, again, a process of evaporation used to cool something. But really what a heat pipe is doing is it's moving heat from point A to point B. It still needs to get out of your system. So you generally attach a heat pipe to a fan, and then the fan blows it out. There's also things called vapor chambers. Vapor chambers are these big flat pieces of copper that essentially do the same kind of thing as a heat pipe, but they're spreading the heat out. They're giving it more surface area. And again, you use a fan somewhere along the line to then evacuate that heat out. There's things called heat sinks, which you're probably familiar with. They look like these, finned things that you clip on top of hot pieces to act as a radiator. The radiator in your car is a great example. It's got it has a fan associated with some kind of liquid movement across some fins. And again, all these things have been around for freaking ever. Just imagine, and this is the challenge that a company like Ventiva has when we show up. We show up and we say to a thermal designer, hey, all that stuff that you're doing, we're going to change it a little bit so that you don't do it the way that you're doing it right now. We've got a bunch of benefits that we bring to the party with that, but chief among them is we don't maintain this kind of weird semicircular shape that a fan does. We're like a little rectangle. So you pop this thing in your system and it'll help you move the air. It'll do it without noise or vibration, and it'll enable you to build thinner, more quiet type devices. Well, but the challenge for the bulk of the industry is the fact that at the very base of this, the inefficiency in some design shows up as waste heat. But when I say inefficiency, I don't mean that as to cast an aspersion on a system designer. We're just talking physics here at some point. There's a fixed amount of energy in the system. Energy cannot be created or destroyed. It just changes. And one of the ways that energy changes itself is heat. So when Ben talks about, these data centers with, 1,000-watt cards in them, he's also talking about a serious heat problem for these guys. So in a data center, for example, they'll take that card. I don't think a lot of people know this. They'll take that card and they're starting to immerse it in liquid. There's this liquid cooling, and that card goes in liquid, and then the liquid is circulated, and that's the way that you get heat removed, right? It's so old and ancient a problem that people don't really think about it anymore beyond, I need a fan to blow air and I need to get heat from point A to point B. And so, true to form, when I was looking at running a business, I thought, hey, let's tackle this one. This sounds easy. We can flip this and make a bunch of money for a bunch of people. This is not easy at all. It is an intractable problem. I don't know if that answered the question, but I'm trying to give you a quick overview of the space.
Yes. No, it's a good setup. Good setup.
So, all right. So let's get to it then. What does Ventiva do? Where does Ventiva fit into this?
Yeah. So I joke about this with everybody here, but in the end, we just blow air. That's all we do. We happen to blow air in a very unique way. We do it by instead of using a mechanical system like those blades that we talk about in a fan spinning, We use electronics to do it. So we're a fully digital system. The way we do it is we have a part of our design that we call the emitter. We energize that emitter, and this is all contained within a housing. We energize that emitter. That emitter forms a plasma around it, and that strips ions from the surrounding air. Those ions are drawn towards a grounded plane some distance away from it, usually millimeter and a half to 2 millimeters. And as those ions move through the air, they collide with other air molecules, and it's just like playing pool. When one billiard ball strikes another, it imparts its momentum, and it transfers that momentum. So the ion moving through the air imparts its momentum on surrounding air molecules. And if you sustain that reaction long enough, you get air movement. What that means for the air movement, though, in particular, is it's fully digital, completely solid state, no moving parts. The most common reaction we get, even from jaded technologists when we show this stuff off, is we hand this over to somebody, they turn it on, and they're like, how the hell did you do that? I mean, like, I feel air moving and I don't feel any vibration. I don't hear any noise. This is the weirdest thing. And it's true. It does. It does kind of have, our technology does kind of have the wow factor. It is absolutely, our technology is impossible to sell over Zoom. I cannot show you air movement in a Zoom call, but I can, I put this thing in front of you and you feel the breeze on your hand. You cannot get over how we did it. That lets you put it in small spots. It lets you cant the thing at weird angles. It lets you break your heat problem up on your motherboard into multiple pieces. So in general, most people designing with fans want to put as few fans as possible in their system. Why? Because, first of all, it's the only mechanical thing in the entire system at this point. It's grease and bearings and all sorts of things that you would think do not belong in a modern electronic system. It's also generally the first thing to break down. It makes noise. It gets dust on one part of the blade and it falls out of whack. It's like it's a difficult thing to manage. So you generally only want one of these in your system. So you're sizing your entire system, or you're building your entire system to accommodate this fan. Some of these fans, today's laptops, are as big as your hand. They're huge, which we can get into in a second. Why have fans conversely gotten large in systems as opposed to smaller? We come along, Ventiva comes along, and we say, why do you need one big fan? Like, you got a hot spot over here on your SSD. You got a hot spot on top of your CPU. You got this thing going on over here. Why don't you take 3 little fans and just gently blow some air over those things, and then we can evacuate it out a side vent or something like that. We break the problem up. We make it look like a semiconductor designer would think about, except we're working in the thermal world. What does a semiconductor designer do? The semiconductor designer does either one of two things. They're trying to put as much functionality in one device as they possibly can, or break the problem up in a way that allows them some degree of modularity in their system, so that they can spread the cost of that thing out across multiple systems. We do that same thing with thermal technology, and it fundamentally changes the way people look at their design. So our design cycle for our stuff is longer than it would be if we were just giving you a simple thing that just moves air. But at the same point, it is not only is it longer, but the payoff at the end is you get these very, very unique designs as a result. Things that you couldn't conceive of having air movement in them suddenly get some air movement. So we scale all the way down to the handset and all the way up to the laptop. We're not really a super great answer for things in the data center. We are not going to cool your 5,000 watt NVIDIA GPU behemoth. But you probably are going to immediately look to us to say, wait a minute, I got a bunch of DIMMs on that motherboard. They're all crammed really close to each other. If I could get air movement between those DIMMs, I'd reduce the heat load on those things and reduce bit errors, for example. We have a play there. But that's in essence what we do, and how we try to go to the problem, go about attacking the problem.
Interesting. That makes sense. I like the approach. Obviously, not having if I'm summarizing what you're saying, it's essentially the feeling of a fanless system, even though the thing needs a fan because it gets really hot.
Yeah,
So
we would. You got it right, Ben. We would tell you that it's not you don't. We're not a fan.
yeah,
Fan is a particular category in and of itself, and it has its uses, but we're not a fan. So yes, in essence, what I can provide you, Ben, is say a 20 or a 25 watt TDP thermal. We can handle the thermals up to like 25 watts, let's say, in a laptop, and it give you an AI enabled laptop that makes absolutely no noise and is super thin. Like, because the other thing about our stuff is, think about this too. Traditional fans, traditional blowers need air space around them to pull in air and push it out. We don't. We're completely linear, laminar. So we take in air from one side and the other. And we push it out the other. So all that space that is kept inside of a laptop in terms of air gaps, we can get rid of. And that sometimes can be 2 or 3
right.
millimeters of the space.
Yeah. Yeah. No, and you obviously see, I mean, there's a couple things, right? So I'll make this point and then I'm just kind of curious. Your solution seems so obvious. Like why doesn't everybody use it, right? I mean, my Vision Pro has a fan in it. Like I'm feeling, air being moved. We're still making laptops in the 18-20 watt range that require fans, and that's not going away anytime soon because again, we want to pack more compute, more AI processing, so we need more performance. But yet, my assumption would be people are just stuck in their own design ways to
Yeah.
just make these chassis changes and move away from a motor roll. Like, is that kind of the big problem you're trying to get over? Is just getting people to
Yeah.
rethink the design of their hardware?
Yeah, there's a couple things there. Yeah, I mean, I guess it's a tried phrase, but it's true. Nobody got fired for choosing an axial fan.
Okay.
Um, but and it's true. Everybody, it is, and I don't blame them when they come hard up against this design challenge. But then you got to ask them a question, right? Um, what is it your customers want? I was in a meeting, executive meeting at a very well known laptop company, and you got the CTO in the room. And these guys are just, these guys, I got 15 executives in the room, and the CTO turns to his VP of marketing and says, all right, what's our number one customer complaint in laptops? And the guy says, it's fan noise, 100% fan noise. And so the CTO turns to me and goes, there you go. I guess we solved that problem with you. And the VP of marketing turns and says, well, you didn't ask me what the second biggest customer complaint was. What is that? Second biggest customer complaint is fan noise. We have the same problem. Like, it's so bad that it actually costs them business. So they have to, that's one of the things that they see as part of their issue. The second thing that they see as part of their issue, which they can't get around, again, this is from the customer side, is this whole sense of we're in a video enabled world. You and I are talking about this over a laptop. I'll out Jay a little bit here before we get on the call. We're talking about, do you hear a little fan noise in the background? Is there something going on in the background? Right. It's actually quite a common problem on Zoom calls. Somebody's fan spinning up to be able to take care of things. If you don't have a headset in, it's going to be trouble. Right. Up to and including all the other things that we do around us where we don't want that little whine in the background. That's one thing is noise. But I think the other thing too that starts to really play into this is the way that systems are designed to accommodate the fact that the only way I have to evacuate air is a fan. Right now, I want to draw a distinction. When you turn a fan on its side and you blow air, you suck it in from the top and you blow air out the side. That's called a blower. So, I'm sure that if any thermal people are listening on the call, they're yelling at me, going, "It's a blower in a laptop," and that's true. You're down to physics. So, if you want your blower to be quiet but also move enough air, you have to turn the blower slowly. And to make sure that it's moving, that has enough pressure to push something out of the system, you use a very big fan and you turn it very slowly. So conversely, we get in this very weird moment where in order to make a fan as quiet as we need modern systems to be, it starts to take up more and more of your motherboard space, which means you get less battery in your system. And if we're talking about portable systems, and it also means that you're decreasing the amount of area that you have to do other useful things in the machine. You're trading it off to just be able to cool something. I come along and I'm like, I don't know, a third the volume in general of this stuff. The more you use our stuff, the better it gets. And our technology is starting to return some degree of design flexibility back into the system. And that becomes really, really compelling. So I just don't want to say it's only a noise thing. That shows up, I want to tell you, that shows up everywhere. This balance point between putting in a fan and trying to get some cooling versus the functionality of the system is a huge issue. And of course, if you pause for a moment, if we think about the market applicability of this, you pause for a moment and you think about the sheer number of things that you encounter in your day that have a fan in them. And then you imagine that I'm trying to take just some of that. We have a very, very large market opportunity in front of us if we do it right.
So that was going to be my next question. So what is the opportunity? Like, what kinds of products are you seeing traction in today, and where do you think you can take it?
Yep. So I think the first one that you'll see our stuff in is probably going to be laptop devices. What used to be laptop computers, what used to be for us, what was considered a 10 to 15 watt problem, all of a sudden is like a 15 to 20 watt problem, and a 15 to 20 watt problem is not like a 20 to 25 watt problem. And we're getting even more pressure to develop systems that develop technologies on our side that support that kind of thermal load. The reason is everybody's trying to shove AI out to the edge. Everybody wants a laptop that's got some LLM capability in it for all the reasons that everybody's super excited about artificial intelligence. And the more that we say we can support that, the happier our laptop customers get, because they've already been staring at if you're looking at an Intel system or an Intel-based system or an AMD or a Qualcomm-based system, you're staring at stacked inefficiencies that lead to a massive thermal problem for the laptop companies. They struggle to do what are they going to do with the heat load that they're facing, and now you just layered AI on top of it because it's the thing right now. You got to have that capability. That's our market. What does that look like to us in terms of unit volume between now and 2025? There's a cumulative. There's that market total is like 300 million units worth of stuff for us. Very, very rich market, in a market that absolutely does not have an answer around silence and size and unique form factor, and we think we deliver that.
Yeah. Yeah, because the reality is the answer, and this is where with a lot of the work that we do with the PC OEMs, I always ask, like, what wattage is this running? Because I know what their threshold is in order to not have a fan in a system. And you're kind of like, well, all right, if I need it to be sub 20 watts, I can only do so much with this product. And exactly like you said, right, we want to pack AI. We've got, even the leading edge process is not the answer, because you still have to keep, Apple's latest M3 in an Air still has to be in the 20 watt range in order to not, have a fan or sub 20 watts. So you're kind of like, well, we want to do these things, and our hope is, well, next generation we'll get power efficiencies at 2 nanometer, and it just doesn't happen. Like that trend has not gone away. So the problem does not go away, let alone in laptops. And then again, I said, if we're going to have face computers, goggles or helmets, again,
right. Well,
we're packing compute there.
Think about that one for a second. That's one of my current favorite examples, right? So now we're going to strap a computer to our head, and we're going to put that computer on our head, and we're going to put a fan in it, and that fan is going to vibrate. And let me tell you, your head is exquisitely sensitive to any kind of vibration attached to it, right? So I don't want it to spin fast enough to create vibration. So I have to slow it down. And in order to make that thing useful, the fan gets bigger. This is just physics. This has nothing to do with me, right? On top of that, I'm going to put a rotating thing on my head. Like your neck will pick up gyroscopic effects much more sensitively than you think it's capable of, right?
Right.
So you
Right.
get all of these things going on. Every time I hear somebody, complain about any one of these things, I start licking my chops because, like, yeah, I got an answer there, and I have an answer that ultimately solves those kinds of problems in the way that you want it to be solved, which is I let you choose the size. I let you move the pieces around. Our stuff is designed to kind of be like Legos. You can gang these things up. You can put them end to end. You can make them at little angles. You can do all sorts of things to solve your heat problem. And it takes the thermal problem, it moves it from what we try to do is take the thermal problem from the back end of somebody's system design. This is normally how it goes, whether it's laptops or headsets or whatever. In general, somebody shows up on the poor thermal engineer's desk and says, "Okay, we developed our laptop. Please now remove 25 watts of heat from this thing." And it's at the very end, and you've got this much space. Here you go. What we try to say is like, look, it'd be much, much better if we did this starting at the very beginning as part of the entire industrial design process. Now you can think about how you want this thing to behave and where your hot spots are. And I don't need to cluster them near where the airflow is. And I can do all sorts of crazy things with it. That's what we try to show up and do.
Sure.
But yeah, I think you nailed it, Ben. That is everybody thinks that the problem is going to go away by moving to 1.8 nanometer or whatever Intel's whatever it is, obscure lake or whatever their latest processor design. I can't keep straight of these guys anymore. But whatever latest processor design they're coming out with will somehow fix my thermal problem, and it never does.
Yeah. Yeah. So broadly wise, I mean, you hit a little bit on, people have a traditional approach to manufacturing. Is there, you have an approach you just articulated, and I appreciate the difficulties of trying to convince people to do something new who are stuck in their ways. That's a industry age old problem. Are other than the approach that you guys take, and then a traditional fan, are there
Mhm.
other things happening out there for thermal management? Whether again small devices or big devices, that's not a fan liquid. I mean, are there other approaches even beyond
Yeah.
what you guys are doing?
Yeah, so our approach uses electricity to move air. There's other approaches to, and I'm kind of differentiating between those things that move heat from point A to point B. So I'm thinking things like heat sinks or vapor chambers or heat pipes. That I'll put that in a separate category. In terms of what I'll call the active air movers, there's another company out there that is doing some really really exciting work called Furore, Frore. They have this uh, great pedigree, bunch of Qualcomm guys, and are doing some really exciting things. Their approach to actually moving air uses piezo, meaning a vibration, albeit and I'm going to describe this poorly because it's not my product, and I hope I do it. I hope I do it justice. But basically, they've developed a process whereby by moving things up and down, and in sequence, I can get some air. I can get air movement that is enough to be useful. From what I've read about the technology and what I understand about it, it's super interesting, and an amazing chunk of engineering went into making this work. The thing that's particularly interesting about it, not the technology, but the company and the space for me, is seeing other companies pop up into the space and get funded. And they're really well funded, and they got an absolutely huge team working on this stuff. Tells me that there's need, the market is looking for alternatives. The market needs things out
Sure.
there in order to address this, and so every time I see them getting some press or getting some coverage, I'm like, go 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 go, because it's a huge market, and that rising tide raises our boat.
Hmm.
So that's I will tell you, that's the only other one that I'm aware of. We're
Okay.
the only ones out there doing anything with EHD,
Okay.
as far as I know right now. And we've been, I think I mentioned this, we've been pretty careful about how we protect the IP around stuff like this and make sure that we can have a good moat sitting around the technology as we go forward. But those are the two things that I see going on right now.
Yeah. So you mentioned, right, you're not quite a data center solution. Maybe someday you will be, but there's obviously like devices. Where else do you go from here? Is there an automotive play? I mean, I
Yep.
would imagine that there's, to your point, a threshold in wattage that kind of becomes what we're doing can attack this problem that takes you up
Right.
to here.
Right.
But what about other areas? I mean, I imagine that
Well, yeah,
cars might have subsystems, etc.
yeah, okay. There's a couple of things, and I should say that we try. Remember, I told you at the beginning, we try to look at the problem as breaking it up, right?
Right.
So I can imagine, and we imagine systems that have massive heat problems in a bunch of areas, and we cool some of it one way, and maybe use a blower to
Right.
cool some of it another way. So there's some markets where we just look at it and we go, no, we're not excluded from it, but it's not an emphasis
Sure.
for us in
Sure.
general, right? And that includes things like the data center and all the rest of it. We've done so of the stuff we're working on right now. We're working on a handset design right now with a well-known handset company, and it's early days, and you can't. I don't want to say that we have a perfect answer for it there yet, but what we were looking for all along when we started figuring out how to put this kind of stuff in a handset was somebody who would partner with us on the bottom up design. It
Mm.
wasn't us
Hmm.
retrofitting into an existing handset. We needed to
Right.
think about how a handset took advantage of our stuff and all the rest of it. What the implication is, as you can guess, is that we can get really, really small. And the thing that's super interesting about that is the smaller we get, the better we look. And it's down to physics. Like you try to imagine any kind of blade pushing air at a very small size. The physics get very bad for them and very, very good for us. So we like ultra small things, and of course that market is beyond large. So we there, and then at kind of the top end of things that we've been working on is large format displays. So call it an 8K TV.
Yeah.
Mass. Here's it is a perfect problem for us. You get this massive heat problem in large format displays because you have things like upscalers and ASICs in there that are just you turn those things on, and they just throw off heat. Now imagine those semiconductors are in the center of an 80-inch display. There's no way to get the heat to the edge. Literally no way to get the heat to the edge because the edge is like 20 inches in one direction or something like
Right.
that.
Right.
Plus, the second part of the problem is you mount this thing on a wall, and if you put a fan in there, the wall acts like a speaker. So the vibration of the fan pushes the noise back towards you, the user, and nobody likes that either. So we come along and we go, well, here's what we can do for you. We can push air towards the edge, or how about this? We could turn every single one of or any one of your grills on the back of your TV. We can turn that into an air mover. So some of those can push, some of those can pull, and we can actually kind of duct air around inside your system completely silently. Which you can imagine if you're a we start talking like this to a TV manufacturer, and everybody in the room just vapor locks. They have no idea what to do when we say this. Like, you can put two here and one there and one at this edge and do this
Right.
and that.
Right.
Like, what the
Right.
hell?
Right.
But again, we have an answer there. Or I would say, kind of in the more traditional realm, in some of these areas, these guys are all using heat sinks. We take a heat sink and we attach one of our ices to the fin stack on the side of the heat sink. We make it literally no bigger, but we increase the thermal effectiveness of that heat sink by like 10x because we're blowing air through the fin stack, right? So we haven't increased its size, but we increased its performance. So we lower its weight, we can reduce its profile, et cetera, et cetera.
Yeah.
And that's we're doing that all with like like 18 guys and some burritos on Friday.
A lean machine.
We are a
Well, this
lean
this is super
machine.
interesting, and I know we're closing, but I want to make this point because I think this is a relevant way to think about, at least the way I think about this problem. Everybody, because we work with devices OEM after device OEM on products, and I always appreciate how many compromises in compute need to be made to hit a form factor. And so
Mhm.
being able to say, I can make something that's the thinness and lightness of like a MacBook Air, but have it be 25, 30 watts is actually pretty interesting because you couldn't
Yeah,
do it before, right? In
correct.
that chassis. So I
Yeah,
like the way you've approached the problem, and I agree with you. I think there's lots of compelling applications, like we talked about face computers, right? People are diminishing the chip in a headset because they have to. They can't. I mean,
right.
Apple put an M2 in it and cooled it, but they're Apple, right? They're not. Other people would love to do that, but they can't. So having that new approach to design, I think, is exciting because again, the vendor doesn't have to make compute trade-offs to get the value in thinness and lightness in a handheld and a face worn in a laptop. So that's an exciting proposition in my opinion.
Yeah, what I was going to say, Ben, to that is just so you know, I think we've delivered by probably by next week. I think we've delivered 10 different laptop designs that are all 20 to 25 watt and completely silent and can are looking at new form factors and all the rest of it. And I should tell you, the other fascinating thing about this is we take their laptop design and within about 5 days we return it to them completely transformed by the underpinning of the technology. We're removing their fan and putting our stuff in there.
Mm.
Um, and the reason I say that the 5 day thing is not to just say that we're really clever about this. I think the thoughtfulness of our design, the way we've approached it, allows us to be able to turn these things very quickly and put in in customers' hands something that they can go off and start playing with almost immediately as they start deciding on what trade-offs they want for a next generation system. And I don't know of a lot of thermal technologies
Yeah.
that can do that right now. There are nobody's showing up with a heat pipe
Yeah.
and says, "Hey, try this one out." You have to design a system around it, right?
Right. Right.
So I feel pretty good about our prospects, but it's a this I again back to what you guys said at the beginning. The fact that you're even talking about this is a big deal, not just for a small company like ours, but bringing awareness to the fact that the war on entropy is never ending is a big deal. That is a really big deal. So you guys get, I think, very big props for bringing it up as an issue.
Yes. Well, this was a rich discussion. We greatly appreciate your time
No
and your
worries.
insights, and encourage everybody to follow along in the Ventiva journey. Check them out if you haven't, and we will catch up with you next time. Thanks again,
Excellent.
Carl.
Great having you guys. Great talking to you guys. Have me on anytime. I'm happy to talk.
Thanks a lot. Thanks everybody for listening.
Be well. Thank you.